displacement x, velocity v, acceleration a, and time t are related. Let's derive how each term is related to the other. Before deriving the kinematic equations, we have to learn about a, t, and vt graphs. You know that acceleration can change with time and the position of the body. Here, we will deal with bodies moving with constant acceleration. VT graphs help us understand the given problems a little more clearly and solve them easily. Let us look at one interesting aspect of the VT graph. This graph actually helps find the displacement of a body. Let us consider an example where a body is moving with a constant velocity, v, during the time interval, t, where t is equal to t0 is equal to 0 to t is equal to t1. Let us draw the VT graph representing this motion of the body. We get a line parallel to the x-axis. We know that velocity of a body is the ratio of its displacement and the time interval. We can say that displacement is a product of velocity and the time interval. This is the product of velocity v and time interval t1. This is nothing but the product of the height and the length of the rectangle formed when a line is dropped perpendicular to the x-axis. That is, the area of the rectangle. The area under the line up to the x-axis indicates the displacement of the body. The same concept applies to bodies moving with a constant acceleration. In this case, the VT graph will be an inclined line, and the area under this inclined line up to the x-axis represents the displacement. There are three important kinematic equations for uniformly accelerated motion. Let us derive these equations one at a time. The first equation is the relation between initial velocity, v0, final velocity, v, uniform acceleration, a, and time t. The velocity of an object is v0 at t0 is equal to 0 and v at time t. Average acceleration, a dash, is the ratio of the difference between v and v0 and the difference between t and 0. The value of a dash is equal to acceleration when acceleration is constant. By cross-multiplying and rearranging, we get the value of velocity as the sum of v0 and the product of a and t. This is equation 1 of motion. The second equation represents the relation between displacement x, initial velocity v0, acceleration a, and time t. The area under the line PQ up to the x-axis represents displacement x. Displacement x is represented by the area between the lines joining points O, P, Q, and S. This is equal to the sum of the areas formed by the triangle PQR and the rectangle PRSO. We get the value of x as half the product of t, and the difference of v and v0 plus the product of v0 and t. From equation 1, the value of v is the sum of v0 and the product of a and t. Here, the value of the product of a and t can be derived as the difference between v and v0. Now, replacing the v minus v0 in the equation by at, we get x is equal to v0 into t plus half at square. This is equation 2 of motion. The third equation is the relation between initial velocity v0, final velocity v, acceleration a, and displacement x. The average velocity of a body v dash is half the sum of v and v0, where acceleration is constant. We know that displacement is the product of average velocity and time. That is, the product of v dash and t. From equation 1, v is the sum of v0 and at. By rearranging the equation, we get time t equal to the ratio of the difference of v and v0 and a. Substituting the values of t and v dash in the equation for displacement, we get x equal to the ratio of the difference between v square and v0 square, and twice the value of a. By rearranging the above equation, v square is equal to v0 square plus 2ax. This is equation 3 of motion. Let's now use calculus to derive the equations of motion that were derived so far using basic mathematics. The new set of equations we shall derive is very useful in solving complicated problems. Let's start with uniform rectilinear motion. Observe the xt graph. t0 is not equal to 0, and x0 is also not equal to 0. dx by dt is equal to v, which is a constant. Initial values are x0, t0. Final values are x, t. Cross-multiplying equation 1, we get dx is equal to v into dt. Integrating both sides, we get integral x0 to x dx equal to v into integral t0 to t dt. We get x minus x0 is equal to v into t minus t0. On transposing, we get x equal to x0 plus v into t minus t0. This equation is used to obtain the position coordinate x of the body at any time t. This equation can be used when the values of x0 and t0 are both or either of them is equal to 0. In other words, the equation is applicable under all conditions. Now let's derive equations for uniformly accelerated rectilinear motion. In this type of motion, the acceleration of the particle is a constant dv by dt is equal to a, which is a constant. The initial values are x0, t0 and v0. Similarly, the final values are x, t and v. dv by dt is equal to a. By cross-multiplying, we get dv equal to a into dt. Integrating both sides, integral v0 to v dv is equal to a into integral t0 to t dt. v minus v0 is equal to a into t minus t0. Rearranging the equation, v equals to v0 plus a into t minus t0. This is equation 1 of motion. We know that dx by dt is equal to v. Substituting this value in equation 1, we get dx by dt is equal to v naught plus a into t minus t naught. By cross multiplying, we get dx is equal to v naught plus a into t minus t naught multiplied by dt. Integrating both sides, we get x minus x naught equal to v naught into t minus t naught plus half a into t minus t naught whole square. This is equation 2 of motion. V is equal to dx by dt and a is equal to dv by dt. From equation 1, dt is equal to dx by v. Substituting the value of dt in equation 2, we get a equal to v into dv by dx. We know that this value of a is a constant. By cross multiplying, we get v into dv is equal to a into dx. Integrating both sides, we get integral v naught to v. V into dv is equal to a into integral x naught to x dx. This is equal to half v square minus v naught square equals to a into x minus x naught. Rearranging the equation, v square is equal to v naught square plus 2 a into x minus x naught. This is equation 3 of motion. We know what displacement is. Now, let's understand what relative displacement between two bodies in rectilinear motion is. When several bodies move independently along the same line, time should be recorded from the same initial instant for all bodies, and displacements measured from the same origin and in the same direction. This implies that a single clock and a single measuring tape should be used. Let's consider two bodies, A and B, moving along the same straight line. At an instant, their position coordinates are x, A and x, B respectively. This implies that A is at a distance x, A with respect to origin O, and B is at a distance x, B with respect to the same origin O. This implies that the distance is measured with respect to the fixed point O, which is the origin. X, B minus x, A is the relative position coordinate of B with respect to A and is denoted by xb by A. When both A and B are moving, we take the distance at a particular instant. Differentiating relative distance xb by A with respect to time, we get relative velocity, which is denoted by vb by A. By differentiating, we get vb by A is equal to vb minus va. Coming to the sign convention, regardless of the position of the origin O, with respect to the positions of A and B, a positive sign for xb by A means that B is to the right of A, and a negative sign means that B is to the left of A. A positive sign of VB by A means that when B is observed from A, the motion of B is in the positive direction, that is, rightward direction. A negative sign of VB by A means that when B is observed from A, the motion of B is in the negative direction, that is, leftward direction. This concept can be applied to determine the relative distance and relative velocity. Let us consider a few cases where two cars are traveling on a straight road with varying velocities. Case 1. Cars A and B are moving on a straight road with equal uniform velocity of 10 meters per second. At the time of initial observation, that is, when TB0 is equal to 0, B is 40 meters behind the crossroads, and A is 20 meters in front of the crossroads. What is XB by A and XA by B at time T0 equal to 0? Taking the crossroads as the origin O and time equal to 0, XB by A is equal to XB minus XA. This is equal to minus 60 meters. Minus sign indicates that the car B is on the left side with respect to A. XA by B is equal to XA minus XB. This is equal to plus 60 meters. Plus sign indicates that the car A is on the right side with respect to B. 2. What is XB by A and XA by B at time T equal to 5 seconds? Here, VA is equal to 10 meters per second. XA O is equal to plus 20 meters. TAO is 0 second and TA is equal to 5 seconds. We need to find XA. XA is equal to XAO plus VA into TA minus TAO. On substituting and simplifying, we get XA equal to plus 70 meters. Calculating for XB, here VB is equal to 10 meters per second. XBO is equal to minus 40 meters. TBO is 0 second and TB is equal to 5 seconds. XB is equal to XBO plus VB into TB minus TBO. On substituting and simplifying, we get XB equal to plus 10 meters. Now, calculating for XB by A, which is equal to XB minus XA. On substituting values and simplifying, we get XB by A equal to minus 60 meters. And calculating for XA by B, which is equal to XA minus XB. On substituting values and simplifying, we get XA by B equal to plus 60 meters. We observed that XB by A and XA by B are same in magnitude. This implies that the distance between the two cars remains constant, irrespective of time elapsed from the first observation. What is the relative velocity of B with respect to A at time t equal to 4 seconds? We know that the values of t, VA and VB are equal to 4 seconds, plus 10 meters per second and plus 10 meters per second respectively. As the two cars are moving with uniform velocity, VB by A is equal to VB minus VA. By substituting and simplifying, we get 0 meters per second. When and where the two cars come side by side? By comparing the results of the first and the second bits of case 1, we can say that the cars never come side by side. Case 2. The position of the cars at initial observation being same as in case 1. Now, car A has uniform velocity of 10 meters per second. And car B has uniform velocity of 20 meters per second. 1. What is VB by A and VA by B at time t equal to 4 seconds? As A and B are moving with different uniform velocities, the values of t, VA and VB are 4 seconds, 10 meter per second and 20 meter per second respectively. Here, VB by A is equal to VB minus VA. On substituting and simplifying, we get VB by A equal to plus 10 meter per second. Calculating the value of VA by B, it is equal to VA minus VB. On substituting and simplifying, we get VA by B equal to minus 10 meter per second. 2. When and where the two cars come side by side? When the cars A and B come side by side, their position coordinates with respect to the origin must be the same. That is, XA is equal to XB. This can be called equation 1. Here, XA is equal to XAO plus VA into T minus T naught. By substituting and simplifying, we get XA equal to 20 plus 10T. This is equation 2. Similarly, XB is equal to XBO plus VB into T minus T naught. By substituting and simplifying, we get XB equal to minus 40 plus 20T. This is equation 3. Substituting equations 2 and 3 in equation 1. On further simplifying, we get T equal to 6 seconds. This is equation 4. Further substituting equation 4 in equation 2, we get XA equal to 80 meter. The two cars A and B come side by side at 6 seconds when their position coordinate is 80 meters. Case 3. At the time of initial observation, that is, when T naught equals to 0, car A is 40 meters behind the crossroads, and car B is 90 meters ahead of the crossroads. Car A is moving towards right with a uniform velocity of 10 meters per second. Car B is moving towards left with a uniform velocity of 15 meters per second. 1. What is VB by A and VA by B at time t equal to 3 seconds? VB by A is equal to VB minus VA. By substituting and simplifying, we get VB by A equal to minus 25 meter per second. Similarly, VA by B is equal to VA minus VB. By substituting and simplifying, we get VA by B equal to plus 25 meter per second. When and where the two cars cross each other? When the two cars cross each other, their position coordinate is the same. That is, XA is equal to XB, which is equation 1. Here, XA is equal to XAO plus VA into T minus T naught. By substituting and simplifying, we get XA equal to minus 40 plus 10T, which is equation 2. Similarly, XB is equal to XBO plus VB into T minus T naught. By substituting and simplifying, we get XB equal to 90 minus 15T, which is equation 3. Substituting equations 2 and 3 in 1, we get T equals to 5.2 seconds, which is equation 4. Substituting equation 4 in 2, we get XA equal to 12 meter. Therefore, the two cars cross each other at 5.2 seconds when the position coordinate is 12 meters.